Good evening, everyone. Thank you, Marek, for the introduction. I'm sorry that some of you are hidden behind the pillar. Hey, and hi. So I have a broad range of you guys. So I don't know if I can catch all of you by my eyes. So sorry for that. Before I start the talk, is there anyone who doesn't speak Czech? Okay, perfect. So the English language is in place. So everything will be in English. Okay, so let's start with the topic. I attended a few MLMU talks, and I really like the topics from machine learning. However, our company is working on a little bit different thing. We develop things or systems which we call decision support systems, and we are typically utilizing optimization. And when I started to think how or what role machine learning plays in our systems, I got quite interesting thoughts and questions, and I don't know the answer. And basically, I'm here to ask the questions, iterate through some thoughts, and present some approaches we took to overcome some challenges. However, there is no finite answer, and I would like to discuss the open issues with you after. So why I'm talking about integration of machine learning and decision support systems? Because we do this for a number of years in our company. Basically, we started with providing solutions in like typical domains like logistics, supply chain management, strategic optimization, meaning like randomized asset allocations, physical security, cyber security. And then the guys at the companies ask us, we need to analyze the data, we need to get some insight, and based on that insight, we need to decide. So we started to also apply machine learning to these problems, to basically, for example, to improve the logistic process. We need to get some insights into how the customers behave, what the trends are, and what are the forecasts to base the logistic model on. And actually pretty early we encountered quite fundamental problems, how to merge the outcomes from machine learning with optimization models. And there is a huge wave of deep learning which is trying to solve everything, and I actually was struggling basically where is the line between optimization and machine learning, as optimization approaches are typically used in machine learning to, for example, train the models. So we can discuss that a little as well. Before we do that, I would like to borrow a pyramid from IBM. I think it's like 20 years old, and IBM had this vision what to do with the data in the companies, and they created this sort of pyramid which allows us to basically cluster the things we can do once we have data in place, and basically get from the bottom layer to the very top, where at the bottom basically the companies are struggling how to put data together, how to put them into databases to actually start some thinking over the data, and we are not really interested in that, and it's typically being solved. The second level is some sort of descriptive analytics. Simply said, it's some sort of a visualization. So you can imagine business intelligence platforms which are providing some sort of insights into raw data. And over that, you can build more sophisticated models which provide better insights like forecasts, interpolations, classifications, clustering, and so on, where basically the interesting machine learning starts, right? And on the very top is prescriptive analytics, which is basically telling the guys what to do, right? So basically this is the fear of AI taking over, where we are automating everything, and instead of humans, the computers are deciding. So if you imagine, for example, air traffic domain, there will be no air traffic controllers, but artificial intelligence telling the airplanes what to do, or actually the airplanes can negotiate which way they will fly. So this is at the very bottom, and there is nothing above. Basically, once we are there, that's the singularity, right? And everything is done. We are not there yet, and one remark is that I really find the naming of prescriptive analytics unfortunate by IBM, because when I'm attending their workshops, they are like, you know, we have a number of analysts doing machine learning, so they should start with prescriptive analytics. And it's a completely different thing, because you need to use completely different set of tools. And here lies the difference I want to focus on, and look how the predictive and prescriptive analytics play together. Before actually diving deeper, I want to provide a few examples which are in these three layers, and I have the pointer, so I will try to use the pointer. Okay, these three layers. So as I was talking about the visualization challenges which are being solved by Good Data, Tableau, other business intelligence tools, I took the major segments from their websites, which is typically financial services. You have a lot of financial data. You want to see what's happening. In retail, you have a lot of products. You want to see, you know, the prices, trends, and so on. Nothing really sophisticated. And in healthcare, it's the same. You want to see all the data relevant to your patients. Machine learning, which is this guy, is pushed quite heavily by our gigantic companies, providing us sometimes with some open source solutions like Google, Amazon, Facebook, and the stream of data which is being processed are images, video, speech. However, also, let's say, personal data or customer data, and they are typically used for personalizing the content, being it recommendation of movies and so on. So these are like classical algorithms for of machine learning. And then there is this special thing typically in old industries, I would call them, or traditional industries, like supply chain management, inventory optimization, production planning, manufacturing, workforce scheduling, and so on, which are actually being solved for tens of years. And they are actually on the top of the pyramid. However, there was no SVM being applied when, during the Second World War, there were the logistics model being applied, right? So there is no prerequisite of doing this before this. So there is a lot of, for example, supply chain management tools and models in place without machine learning. And the question is, can I inject the thing I learned from past data into these rigid models to improve them? And the answer is yes, and we tried that, and it's quite fun. And I will show you how we did that in a minute. Before I start, I posed the question, what is the difference, right, between machine learning and optimization? And I actually Googled this query. I get a lot of discussions, and some of the guys were telling me that optimization is typically used in machine learning to train the model. We are minimizing some error on train or test data. There is some criteria we want to minimize. So basically, there is a optimization within let's say machine learning approach. However, I'm thinking about the optimization as some sort of a mathematical programming approach, where you have a criterion, you have the set of constraints, you have the variables, and you are looking for the optimal values of the variables such that the criterion is typically minimized, right? And for this, you need typically more or less data. The more modern approaches, the more data you typically need. For optimization, you actually don't need any data to develop the model, right? For traveling salesman problem, you don't need thousands of instances to create the model. You basically formalize TSP, and then you get one data sample of TSP, like the Czech Republic cities and the road network, and you solve it. So you don't need anything for, let's say, solving the optimization tasks. And this is, I would say, the fundamental difference. The question is, when you have a lot of data for optimization task, whether you can do something with that, with the data. And let's have a look at some examples. And I'm talking a lot about logistics. I think I can talk about Crocodile, our favorite company, providing very healthy baguettes and sandwiches. They were planning with pen and paper on a map. We were quite surprised, so we created them this logistic planning tool. So now the baguettes delivered to you are planned by a great software, and there was a lot of optimization to be done. However, what was also very helpful for them was actually to see their data and actually drill down into various customers and problems with deliveries, such that they can actually see that on this route, these 4 customers are not really profitable. And if I take them off, I can save on the logistics, and actually I can make more money, right? Because there are not many baguettes being sold in Jizerské mountains or somewhere there, and it's really far from Prague. So basically they were able to additionally optimize something outside of the logistics model thanks to the data insight. We did a prototype of production planning tool, like typical thing. You have a factory, you have a lot of stuff coming in, a lot of orders, and basically you want to schedule these orders to be manufactured on a line A or B or C. You want to group them together, you want to meet the deadlines. So some sort of a like typical production planning problem. We took a typical production planning model. It was a really big model, so we had some troubles with the computation, but at the end we were able to provide these plans. The problem was that they needed a really good forecast, because there was a lot of orders coming in, and basically every reassembly of the line was really expensive. And they want to do the reassembly only once in a time, so they want to forecast, what will come in, and basically schedule the reassemblings for the future. And we basically took historical data, so some trends, like fundamental trends, and we were able to help them with that. So basically one of the inputs of the optimization model was a forecasting model based on historical data. It was some sort of a multiple trend analysis and trend decomposition, nothing really fancy using networks or anything. It might be possible to do it with deep learning. So this was one very nice example when there was a nice fit. Another one fit was in a project for workforce optimization. You can imagine that you have in China hundreds of factories, and these factories are producing, for example, shoes or t-shirts, and these shoes are sent to Europe, to Lidl, to be sold to some guys, and Lidl wants a certificate of quality. So there is a company with hundreds of inspectors visiting these factories continuously and basically monitoring that the quality adheres to the regulations of European Union before the products are shipped. And the issue is that the inspectors are periodically visiting these factories and they need to have a plan. So basically we provided this company with a scheduler who is scheduling the inspectors where and when to go. The problem is here that the Chinese factories don't have our schedulers, and they typically replan a lot, so they typically reject a lot of tasks. So we planned a thing, and we knew that 30% of the customers will reject or reschedule their planned inspection before actually the inspection will happen. And that's why we created the model of the behavior of the customers, and we injected this model. And basically, then we scheduled with respect to the model. And for example, for some requests, we even didn't consider them because we know almost certainly that the customers will actually cancel and will reschedule a couple of times. So we were able to actually ignore some of the stuff, some of the requests, and actually provide more compact plans with less rescheduling. And that was really welcomed by the inspectors, because there was a Chinese guy calling his wife that he will come home 2 days late because there was some rejection and rescheduling. So then actually everything could work more efficiently. So these examples are simple ones. And then there are more difficult examples. And here in this project we did for an American startup, I would say we didn't fail, but we encountered some fundamental problems in merging the optimization framework with data. And actually, I am happy to have this talk because I actually structured the thoughts about this, and I would be really interested in what you are going to say. So the case study is predictive policing. Before I dive into this, it is important to understand a little bit about game theory. And I checked the machine learning meetups program. Last year there was Branislav Boshansky having a talk on applied game theory, and I don't know how many of you attended the talk. Okay, a few of you. I thought that. Okay, so I will have a few slides about game theory, so we understand what it is. Basically, game theory is nothing really fancy. It's just another optimization problem, but there are, intelligent guys playing against you. So in logistics, there is a set of customers. They don't really care. They just want the baguettes. That's it. In game theory, there is an opponent, and he wants a different thing than you want. So he's optimizing, you are optimizing, and the optimization problem is some sort of a bi-level problem, right? And typically there are multiple steps, so you have some sort of a tree, and it gets really complicated, and there are many unsolved challenges in game theory. This talk is not about game theory, but about necessary background. To understand how the game theoretic problems are modeled, I took a typical example. This is actually one of the first applied game theoretic models in the real world by Team Core at LAX, Los Angeles Airport, in 2007. So basically, the issue was that after 9/11, Homeland Security invested a lot of money into providing security to airports, but they found out that they actually don't have the money, even with Department of Homeland Security, to check all the passengers, all the baggages really thoroughly. So the problem is whom to check with, for example, with dogs for drugs, where to stand with armed forces in case there is some bomb threat, and so on. And we have a really large airport in LAX. I think there are like 8 terminals and a lot of roads coming in and so on. And there are like multiple levels of perimeter patrols and so on. It's really complicated setup. It can be drilled down into a view that I am defending the airport, so let's say I'm the police force, and there are some attackers, right? So there are 2 sides, and typically they want a different thing. The defenders want safety of the airport, and the attackers typically want to disrupt the safety and security at the airport. So these are the players, right? We need to define the players, so we call them defenders, attackers, and then we have to ask, so what are their strategies? And again, we can abstract that a lot. And let's say I have 3 defenders, 3 teams with dogs, and I have 8 terminals. So at one point at a time, I can be in a subset of those 8 terminals, right? And the attackers, I don't know, they have a bomb or something, or they smuggle drugs, for example, and they can be also on one of the terminals, right? So really abstracted, my strategy is how to place the 3 security forces on the 8 terminals. Every 10 minutes, they can, for example, reschedule, or every hour. And the attacker is basically asking, so which terminal I should use for my drug smuggling, because I want to, I don't know, smuggle it to Europe. And then I want to understand the utilities. What are the costs and what are the rewards? And typically I take the strategies. So I'm standing at terminal 1 as a defender, and the smuggler goes through terminal 1. So he got busted, I get reward, and he incurs some costs of the drugs of the guys being in prison, and he needs to send other guys. And basically, if I miss him, I incur the cost of the drugs being smuggled, and he will win the price per kilo per cocaine multiplied by the number of kilos he's able to smuggle, right? So these are the simple utilities, and these models can be more or less complicated. They started actually, so this solution was actually at this level of abstraction. I just wanted to be at some subset of terminals, and before this approach, they were actually rotating the terminals. So every Monday they were at 1, 2, 3, Tuesday 4, 5, 6, Wednesday 7, 8, 1. So when I'm an attacker, I will sit at the airport for a few days, right? I will understand the schedule, and then I will pick the terminal on Monday. I'm smuggling to Europe. On Tuesday, I'm smuggling to Canada and so on, right? So the fundamental thing game theory provides us is randomization. So basically the strategies will be randomized, which is really difficult to explain to the guys, right? You need to toss a coin, and that's optimal to toss a coin. And it will provide me some sort of optimal randomization with respect to these utilities. Sometimes I have very high costs. That's why I will tend to patrol the terminal more frequently, which is, high priority terminal flying over White House. And, the flights over Kansas, I don't really care. So I will be there less. But I will still randomize, such that even though the attacker sits there every day, he doesn't know what will be the schedule for the next day. He can estimate the probabilities, but that's it, right? To compute these strategies, I need to find an equilibrium of a game. This is the optimization problem. To find, I don't know if you saw Beautiful Mind, there was this crazy guy Nash. He got this fundamental result that almost every standard game has some sort of equilibrium, and if I play a strategy in this equilibrium, I'm pretty much safe, right? And there are some nuances, but simply talking, you can see the problem like this. Even more simply, you can imagine that the game can be represented by a matrix. Who is familiar with game theoretic matrix? Perfect, almost half, great. So basically, I have strategies of player 1, I have strategies of player 2, and I'm asking what are the probabilities of playing each strategy, and then I toss this sort of a probabilistic coin once I have the probabilities. And to compute the probabilities, I have to solve this sort of optimization problem. So I'm minimizing some criterion, and there are some constraints, and there are some variables which are the probabilities. Here you can see the probabilities are summing to 1, they are greater than 0, and then I have some constraints which are given basically by the opponent. This is the simplest computation of zero-sum game Nash equilibrium, and I have more complicated equilibria like Strong-Stackelberg equilibria, Bayesian, correlated, subgame perfect, and there is tons more. With different game models, I get very complicated mathematical models. Some of them are unsolved, and some of them are principally unsolvable. So there are some problems in game theory which are undecidable in this computational sense, that for some game models I am basically unable to retrieve any solution, even if I try my best. But let's stick with these simple models I can actually provide a solution to. So basically, by solving the optimization model, I got the probability distribution over the strategies. Then I can, toss the coin, play the strategies, and being placed at different terminals. This is really nice. And it has mathematically proven guarantees. So if I'm selling the product, I can say, if I solve this program optimally, I can say you cannot do better than, this. and they ask us, what data are you using? And we are telling them we are not using any data. And then they are asking, how is it possible? And that's the real question, that they have like tens of years of data collected. And to construct this, you don't really need any data, right? You have terminals, you have strategies, you have costs and rewards, and that's it, right? So I think like the game theoretical model is typically like unattached, or it's not attached to any reality. It's based on some sort of fundamental assumptions which have to hold to actually for this model to be applicable and to be efficient in the real world. And that's the fundamental problem of game theory, that it's basically disattached from reality. Let's start with our challenge we had. The challenge was to provide policemen with some sort of strategies how to patrol Los Angeles. And I took a screenshot from today from Los Angeles Crime Police Department, and these are the crimes which happened last week in downtown Los Angeles. And there are different types of crimes. I think the dollars are thefts, this masked guy is burglary, the cars are GTA, Grand Theft Auto. These are, I think, car thefts or like petty thefts, and maybe there are some rapes or something. Then there are some registered offenders, and if you get really deep, it gets really scary what's happening in LA. If you look closer, what is actually on this map? So here is a USC campus, a very prestigious university. And around USC, there are, students biking around, fraternity, the sorority, parties, stuff like that. This neighborhood is not so nice. Around the highway, there is some sort of a Hispanic majority selling a lot of cars. Then it gets switched to Koreatown. You have a lot of restaurants and Koreans living here. There is a subway line going here along the main road. There is a LA Staples Center. There is a lot of basketball plays and other events like concerts. This neighborhood is again not so nice. This is like the downtown where you have a lot of homeless people and a lot of shops and a lot of commercial places. And then there is Chinatown. I think there is Little Tokyo with distinct patterns and demographics. And when I was in LA, actually I was doing research at USC. I lived here and I was biking, which is really crazy in LA, through these parts. And every few blocks, the neighborhood really changes. And so basically the type of crime also changes as you move around. And this is quite challenging for the policemen because they don't really know what to expect. And an interesting thing is that throughout the years, LA is actually developing, and it's developing quite rapidly. So this neighborhood was really, really dangerous before the USC was based here. And now the rich guys who are paying $40,000 per semester to study at USC are actually renting houses, and they are making them really nice, right? So the neighborhood of USC is steadily improving, and the Hispanic guys are pushed to the north or maybe east, and the crime is also shifting with that. So there is a lot of bike thefts around USC, there is a lot of car thefts here, and I don't know what's happening in Koreatown. The thing is that, if you look at Prague, there were floods, so Karlín got upscale. In LA, these trends are much rapidly observable. So in a few years, the blocks are really shifting. So there is spatial displacement of crime, which is happening, and the policemen are basically patrolling always the same route. And the fundamental question is how to patrol all this stuff and how to provide robust solution for this problem. And there are policemen and there are the bad guys doing different kind of stuff. So it really leads to game theoretic approach. Two players, they have strategies, they have some utilities. Let's model this as a game. It is possible, and basically the solution we took with that company is that we try to collect as much data as possible. So basically, this is not the game theoretic approach, right? But we wanted to understand what is happening. Really important thing for crime is demographics, and we had to be really politically correct for US-based system, but the race was there and there were some correlations, so it was really difficult to communicate that, not to the policemen, they knew, but to the guys higher in the hierarchy. The other trend is, for example, weather. For example, in Montreal, in winter, there are no car thefts. Because you can't really get the car through the snow. In LA, when we got the data, there was no trend at all, and we thought, we got wrong data. But the temperature is basically stable through summer. There are some heat waves which actually cause the people to drink more alcohol, and then there are some more aggravated assaults on the beach and so on. So there is some influence on weather. There is a lot of things happening around downtown LA, a lot of sport events, culture events. The school has some sort of a rhythm, and there is a lot of school events like, the fraternity parties with sorority girls, stuff like that. So the events which are happening around the neighborhood have high influence on the type of crime which is happening, which is typically aggravated assault because there is alcohol involved. But on the other side of the town, there is more cars being stolen, right? Because the policemen are guarding Staples Center because there are LA Clippers fans fighting with LA Lakers fans or something like that. So, the guys of certain race are stealing the cars on the other side of town. Really important part is housing versus commercial buildings. Again, if you imagine cars, burglaries and so on, that happens only in housing districts. Again, some type of crime happens only around subway stations, railway stations and so on, and we know this from our country as well. And there is of course like temporal influence, not really winter, summer, but day and night. Morning, evening, right? So there are not many aggravated assaults in the morning, but in the evening there is a lot, and there is a lot of burglaries at night, not during the day. And we collected a lot of crime reports from different sources. They were actually heavily incomplete, which was quite interesting. So even if we merge the reports, we assume that we have maybe, 60% of the crime captured, and there might be some bias that, for example, petty thefts were not really reported, but car thefts or burglaries were almost surely reported. And so these were all the data, and then we needed to have a model of the criminal behavior, how the robbers behave. And we wanted to use the data for that, right? So we had crime reports, and you wanted to know whether the burglars are more active during the heat waves, or around subway stations, or at night or day, right? So we took the data and we found the trends. House burglaries at night, right? Quite straightforward. On the other hand, we wanted, to capture the thinking of the burglars or of the thieves, using the game theoretic matrix, having the strategies, the utilities, the costs. So we tried to create this matrix again with the numbers, and basically compare the machine learning model with the game theoretic model, and it was really difficult to do. And I will get to that later. Finally, there had to be some sort of a scheduler of policemen, so basically telling them that at this point of time we have to patrol this region, and of course then some sort of a reporting analysis how well we are performing. Sure.
Have you had positions of the policemen in the past, like somehow with patrol?
Great question. No. The question is about the deterrence effect of the policeman, right? So basically what this company was saying, there is a strong deterrence effect of the policeman. If they are patrolling preventively in this neighborhood, there is less crime. That is true, right? But we didn't have access to past data simply because they were not recorded, and there was no scheduler, and the policemen were reactive. They were in some sort of a default patrolling mode, just going around the neighborhood, and then they heard something in the walkie-talkie, or and they followed the crime, and they were deterring the crime along the way, right? We didn't have this data, and the company was saying that it's not really important, but on the other hand, they were saying that their solution had a strong deterrence effect. So that's a great question, that there was a strong bias, and you could say that before it was completely ineffective, and now it's super effective, and you can compare that and so on. And the policemen, the police departments actually invest a lot of money into this solution, so they actually supported this thesis, right, that it helped a lot. So there was a positive feedback from both sides, it works. The policemen were saying it works. So everyone was happy at the end. And there is a lot of questions about the evaluations of the efficiency of the game theoretic solutions in general. For example, how you can validate the efficiency of the game theoretic patrolling solutions for the airport. Because it was in every newspaper. Right? So basically, if you deploy the solution, you will catch less guys. Everyone is scared to, smuggle drugs because they observe the policemen, they don't know what to do, so they don't smuggle drugs, but you don't know. So you caught 10 guys a month before, and now you are catching 2 guys in a quarter. Is it better or worse? No one knows, right? So the evaluation, fundamentally, is extremely difficult because you don't know the other side, what they are doing. And this goes with your question as well. Yes?
Just like a question, why are they publishing the model? Or
So, sorry, what are the...
why are they publishing it in the newspaper? It's secret as anyhow, right?
Because it has the deterrence effect, right? So the policeman at the LAX has the newest modern technology for catching the bad guys. Every drug smuggler will be caught. There are these cases of arrests being made after the system was deployed. It has a really strong deterrence effect. So they don't publish the daily strategies, right? But they publish the news, and then you have the balloon effect, and I'm talking about this later, that they don't use this airport for smuggling. They use the other one for drug smuggling. So actually the Travel Security Agency deployed this sort of game theoretic solution to all the airports in the United States, and no one knows whether it was efficient or not. They paid non-trivial money for that, however, from the Department of Homeland Security. So there might be some indirect proof that it's actually more efficient, or that the money needed to be spent. Yeah, I'm not really, the businessman of that company, so they would talk completely differently. I have some sort of a healthy or unhealthy skepticism to this approach. But actually, the game theoretic approach is the right way to do it. It's not the case that it doesn't make sense. It makes sense. It's the best approach we currently know. The validation is difficult. That's that's all. Let's. Any other questions? Yeah.
When you say it's just to threaten the criminals, in such a case they don't need a model, right? They can just conjure up and say we have a model, and just pretend that they have a super strong system.
Yes. Yeah, and the assumption of the model is that the attackers are actually observing the policeman, at least partially. They see parts of the strategies, and if they announce that they have super strong model and they actually follow the same routes every Monday, Wednesday, Friday, sooner or later the attackers would notice, right? So there has to be at least some change of strategies, and there will be a reaction in the displacement of crime. So for some time I will not burgle the houses because I'm uncertain, and maybe I will switch to cars because there are so many cars that no one can actually handle them. So there, I agree that if you announce something in the news which is fake news and you are able to hide the fakeness of the news, it has the deterrence effect for some time. this solution should have a like permanent effect because the policeman should be unpredictable. And so let's switch the domain and look at the Prague subway. I think the inspectors are actually doing pretty good job in randomization. I don't know if someone is playing, you know, this bandit game on mobile when they observe where the guys are. And I don't have the data, and I thank the guy who invented the application because the inspectors have to randomize more, and they need a game theoretic solution, right? But if you actually are, if you want to play the game against the inspectors in subway, it gets pretty complicated. Like at the end of the year, they don't have the money, so there are less inspections. At the beginning, they are forcing the guys to buy the yearly coupons, so there are more inspections. And there is a reason for that. But even then, sometimes on Sunday, I take a bus or tram, like half empty, everyone is sleeping, and there is an inspector. Like, really. And I would expect them to stay on Můstek and Florence most of the time because there is a lot of passengers coming in and they will be highly rewarded because they will collect a lot of fines. That's not happening, right? So they are randomizing, and from my trivial observation, I can't reconstruct their strategy. Maybe from that application I could have, but even if I have that strategy, it would take some risk to take daily route to work. And at the end, the incentivization is that the risk is so high and the expected cost of the tickets is higher than the yearly coupon which I will buy, right? So I think the Prague subway is doing their job really well with inspections. And no, they don't have our solution yet. So yeah. So that's one of the examples, and even if they announce that now they have super cool solution, maybe some of the guys will buy tickets for some time, but if nothing changes and the application will be still there, they will switch back sooner or later, right? So it's the same problem. Yeah?
Mike, I have a quick question about this validation process.
Yeah.
So is it possible just to observe over periods of times with the same conditions, for instance, the same number of tourists, the same traffic in metro, everything is the same, how well the whole Prague metro is doing? So how many tickets they sold, how many people they catch? So
okay, so let's switch the flow of the talk, okay? This is the problem, and if you solve this, you will be really rich. There is a trend, and this is different problem, but basically that's the problem. There is a trend, there is an event happening, you know, the system is deployed, and the trend continues. My question is whether the event caused the change of the trend and whether the change was positive or negative. If you can solve this, you can trade on a stock market after every event and bet surely on the change, right? So there is a fundamental signal with some trend, and the trend can be arbitrary. There is an event, and the question is whether the trend changed because of that event, with some level of certainty. And if I repeat that many times, I will be right in 51% of the time. Then you will be really rich, right? And because there is no such trading system on the market yet, I would say that this problem is fundamentally difficult. And there are like more or less complicated signals in the general sense. I think the stock market is the most complicated. For example, for traveling or crime rate, which can go like this and then down, you can see that, right? So in singular cases, you can solve this problem. But if you actually want to approach this like generally, to have a general solution for observation how the crime dropped after the deployment of the system in any domain, you would need to solve this problem. So by, I don't know how is it called, proof by showing the difficulty in another domain, I think it's very challenging, and we actually tried to do this for a stock market for different reasons than trading, and it got really challenging. So only for a tiny subset of events which have really tremendous impact, like, I don't know, a bubble crash, like internet bubble crash, right? So there was event like bubble and it went down. Then you can prove that. For example, if there is a cyber attack on a company, or if the CEO actually is exchanged, what was the influence on the stock? It's very difficult. And maybe for a few days, but actually there is really high fluctuation and the volume is increased. So this problem is really difficult. And if any of you is able to provide like insight, that would be great. So this is the challenge of evaluating that system in general. Okay. Yes.
Sorry, I will object against this hypothesis because you always have the chance to prepare the A and B set for testing. You can deploy the system on behalf of the city and have the comparable differences in the behavior of the effort of the deployment on the other side of the city. The problem is on systems where you have incomplete information about the markets. But if you really insist on having the validation, for example, in drug research, I mean the maximum, the distribution of drug research has to prove that the medicine is actually effective, even at the costs of the set B has the increased mortality compared to the set A.
Right.
Because without the validation, it would be just the nice selling of the new tags that your system is superior.
Right.
So, sorry to say that, if you have to validate, you have to prove that your system deploys better, and after being deployed, serves better than another deploy.
That's the ideal setup, right, of the pharmaceutical companies, that they have two control groups. There is no influence between the groups, and they don't know what they are tested for. Yes.
In your discipline,
Yeah.
just about the organization of the AB sets to prove it.
True. And okay. So what I think is that the correlation between the control groups in the pharmaceutical companies is basically one of the diseases, if the sample is big enough. Imagine that you don't have two districts, A and B, but you have two cities, really far away, east and west coast. There is some correlation in crime, which is far from one, right? And you deploy the system in one city. Okay. Based on, I think, some sort of statistic, you can get some statistic hint. But it's far from the pharmaceutical setup. And I agree with you that this is the way how to test it, right? That you have two groups, they don't know about each other, there is no exchange of information, they don't know what they are tested for, there is double-blind experiment, so the policemen don't know which system they are using, there is nothing in the news, and the trends perfectly correlate, and maybe you can find some such cities. And even if they don't correlate, you can find some statistical tools to find the impact. So yes, it might be possible. And the other extreme is like the stock market, where you have two stocks, and yeah, there is one event which can affect the stocks differently because they are different business model. Yeah.
There is a systematic difference because you have incomplete information in the market. The crowd behaves very, very specifically with the limited resource, which is something added to the model which you normally neglect. So
I think there are like two extremes, stock market and like control group settings, and somewhere in between there is the crime validation, partial observable, incomplete information, not perfectly correlating, different dynamics, but there is some statistical correlation, so you might use that, and if they are distant enough, they don't influence each other. Yeah, that would be possible probably. We can discuss that deeper. Okay. Okay. I will switch back to my skeptical view. So we are modeling the crime behavior using machine learning approach, historical data, years long. We know that something has happened more at night and day. So basically, the approach is we take the historical data, we find a model, we generalize over the historical data, and we predict from the model, and everything is very nice until there are some fundamental changes in the city infrastructure which were not captured in historical data. Then we are lost, right? So basically the problem of machine learning approach is that it's based on historical data. What is not in historical data is not likely to be captured by the generalization. Or you can be really general with the generalization to capture unknown things, then the predictions are not very precise, right? On the other hand, the game theoretic approach defines the goals of the players, the strategies, costs and rewards, the rationality model. That's another open question. How rational are the attackers? Are they computing Nash equilibrium every day? Or they see, old lady, so they take the wallet. And there is some rationality, not in petty thefts, but maybe in house burglaries or, this kind of organized crime, gang wars, and so on. Then you have to compute the equilibrium for strategy. And if you compute the equilibrium, I didn't talk about this explicitly, but you assume that the other guy is also computing some sort of equilibrium and is playing the equilibrium or is deviating somehow from the equilibria. So there are some assumptions in the equilibrium computation, so there is also a question mark that it's like questionable, and principally you don't need any historical data. So basically there is this challenge on prediction over a limited data set, and in game theoretical model there is no reality check whatsoever. So what we did is that we took the game theoretic approach and we tried to inject the historical data somehow into that. Let's skip this. So the game is called Bayesian Stackelberg game because it's a game, Stackelberg because the good guys are patrolling every day, the attackers can wait, at some point they can attack. So Stackelberg means that one guy is actually playing the strategy continuously and the other guy reacts on that, which is happening at the airports, with the policemen, and most probably with the inspectors in Prague subway. And Bayesian game means that there are more type of attackers. There are robbers, thieves, guys stealing cars, bikes, raping people, murdering people, and there are different types of criminals. So that's why it's called Bayesian. And you can represent really simply the game as multiple matrices. This is one Bayesian type, let's say car theft. The other type is robbery. There are probabilities, that the criminals are 60% of the time like car thieves, and 40% of the time robbers. They have different strategies. So this guy has only A1, A2. The other guy has 3 strategies, maybe regions. And these are my strategies where to patrol. And I actually switched the numbers. But the matrices can be fundamentally different. And there is, I think, 10 years of research how to solve Bayesian Stackelberg games really efficiently. It's done most of the time by Tambe et al., who is the professor at the USC, who is deploying, these strategies. There are some numbers. There are some probabilities of the guys doing this or that. There are some types which can be inferred from the data. And then there are some rewards and costs which can be also somehow inferred from the data. Typically trying to reflect the incentives. So the machine learning approach can help us to specify the probabilities and the data. And we did analysis of the modus operandi of the criminals. So for example, we knew that the burglaries happen at night with typically 2 robbers based on the crime reports. We clustered the crime types. So for example, there are 2 types of house burglaries. One is opportunistic, old house, door unlocked, I try to steal something quickly, or planned ones during vacations, Christmas time, and so on. We did some temporal forecasting of crime and their influencing factors. So basically, for example, forecasting weather in LA is really simple. Forecasting events is also quite simple because you have the schedule. But for example, the spatial forecasting of crime, the displacement of crime as the neighborhood is changing can be challenging, and there are some fundamental theories from Professor Bertozzi at UCLA, who is actually modeling the gangs in LA and their displacement, and the theory is based on the theory of earthquake waves, and it's really cool, really difficult math based on differential equations, and the visualization is really cool, like the gangs are moving around the city as the waves. Very nice. They created a startup. I think they failed, but the visualization is pretty cool. Okay, so the solution was that we did a lot of analysis of crime and the environmental data sets, meaning the demographics and so on. We extracted a set of rules from the data, and for every day we had this environment model plus the forecast for that given day, that actually it will be daylight and night, for example, or there will be that sort of temperature, or the demographics will actually not change for the day. And we fed this model into the mathematical model, so we changed the constants, and based on the game theoretic model we created a schedule for the police forces. So that was the cycle, and we were kind of satisfied by the result, but actually the fundamental challenge of integrating the machine learning approach based on historical data and the game theoretic approach based on fundamental rationality modeling got somehow stuck on half the way. And I cannot talk about this in Los Angeles, but we are far enough to be honest with you. And there is a question of evaluation, basically, that if you deploy that in Los Angeles, they measure that by the satisfaction level of the policemen, which you can maybe do. And here is the question of the displacement effect. Basically, if you deploy something in one city, the robbers, they don't really move, but what happens is basically the balloon effect, that if you patrol somewhere really efficiently, the crime just displaces somewhere else. And again, this professor from UCLA really shows that if you place the police forces in the middle of the gang, the displacement happens like this, and there is some diffusion, and you need to put the policemen strategically to deter the displacement as well. So there is some long-term effect in the displacement of crime. And if you read Godfather, the book, they destroyed one mafia and moved to a different city. That's the displacement of crime. So yeah, that's another challenge which is there when evaluating the effects of the deployment. I would end here, and the message, right? There should be some message. Basically, I think there is a high affinity to using machine learning in many problems, and it makes perfect sense. I think it's good to think, if the machine learning outputs, the classification or the recommendation of movies or music or blogs to read, is the final result you want to provide to the users, or whether there is something else you can do with the outputs. For example, for the recommendation of movies, I find perfect movies for the guys. There are some commercials tied to those movies. So, and the commercials are paid more or less, and I maybe want to also optimize the costs or actually revenue, right? So I want to recommend relevant movies, but also the movies which generate me the most revenue, or which costs are the lowest. On the other hand, if you are optimizing production or logistics, the question is whether you can actually compute the parameters from past data, whether you can forecast something, or actually whether you can model the behavior of your customers or of your places, or actually trucks in some sense, such that your logistic models and optimization models are enhanced and are more precise. So these are the two questions which I thought are worth think about when you work on your problems. So thanks for all the questions, and we still have a couple of time for other ones. Thanks.
As Ondra said, we have like 10 minutes for the discussion, so if you have any questions, I will pass you the mic.
Hi. I just need a quick explanation to the workflow of your game theoretic thingy. I think it's the penultimate slide, like 2 slides back. Yeah. So does it mean that you have game parameterized by the environment, model, and forecast, and every time you try to find an equilibrium for that game?
Yes, exactly. So basically, the schedule is generated from the game theoretic model by computing the equilibrium. Okay? By solving the optimization model, the mathematical program, I will get solutions for variables. These variables you can imagine as routes or regions where to patrol, right? So I have 0, 1, this region, not this region. The mathematical program has a number of parameters in it, and they depend on weather, demographics, and so on, which might be the same for the day or might be different, and for a given time of the day. So I'm feeding from the data and from my machine learning models these parameters into the game theoretical model, so it changes, and I'm resolving that for every hour, and the regions are slightly shifting, and there is some sort of randomization. So basically there is a probabilistic distribution over the regions, and the probabilistic distribution changes a little bit based on the actual data which are coming from the model.
And what kind of equilibrium are you using as a solution?
That would be the strong Stackelberg equilibrium of the Bayesian Stackelberg game. So, yeah.
So can you do that in real time? Like change it? Because it sounds like this has to be something really fast, and finding equilibrium is not so easy, right?
You can do that in a couple of minutes, I would say, and maybe in a couple of seconds, depending on the complexity, on the number of regions, and actually on the decomposition of the big regions into small regions. And you can say, you know, these police guys patrol only in this big region, and it's actually the case that there are some police regions, and the policemen don't go across some border, which is in the movies, you know, like the car stops at the block because it's out of their competence. So that's there. So the problem is decomposed, so you are not solving the whole LA, but the regions. And within the regions you define like block groups. And for that, there is really heavy research behind that. And there are guys from USC putting a lot of effort. And at the end, the HBS sum solver is able to find that equilibrium, that specific equilibrium, really quickly. At the end, I think it's polynomial. It's not NP hard. If you have the utility structure somehow constrained.
So the equilibrium is exact, it's not an approximation.
Yeah, they can find exact solutions. You can find approximate as well. The policemen are happy, like they want to have provably optimal solution, right? That's the selling point, that you can't be any better. It doesn't really make sense because there is a lot of uncertainties in the data, and even though you are like 0.1% from the optimal, it doesn't really matter because there is such a high uncertainty and missing data and bias that like from practical perspective it doesn't really make sense to compute, but from business perspective it does. And from the research challenge that, you know, you publish papers based on that and you win best papers. Yeah.
Okay, thanks.
Thanks once more. I'm curious, do you update your game theoretical model based on more current data regularly? Do you have some process for that?
Yes, so the system is deployed such that there are scrapers on Amazon Web Service, and they are scraping this data daily, and there are forecasts being generated for next 3 days. Most of the data is static, and there are some forecasts for typically weather, and we are actually taking the forecasts from, you know, weather forecast service. But actually it's like the selling point, you know, that there is environmental forecast, and you can actually generate the the schedule for any point in the future based on this. So there is daily update on the data, but for example, the demographics models that are provided by Census, some sort of a governmental agency, which is updated every 2 years, partially. So some regions you have like recent data, for some regions you have 2-year-old, 4 years old, and even 8 years old, and it's just a sample again. And that's why the optimal computation of the equilibrium doesn't really make sense. The data is imprecise.
Yeah, thanks a lot. But otherwise, you recompute the whole game theoretical matrix daily. Wow.
Yeah, it's a couple of minutes, and there is, I think, Cplex behind that. So basically, you could do that within minutes, and you know the policeman. Actually, so there is additional thing that you want to sample from the probability distribution you get from the computation. So the computation gives you probabilistic distribution, then you have to sample from it. And because you also don't want to leak the samples to the policeman because you are worried that the policeman will leak this information to the criminals, they have tablets in the cars, and the tablets are showing them the next region to patrol, and they don't know which region they will take next, and these next regions are sampled in real time from that computed probability distribution.